Hello world, Burger Bob here. In this video, I'm going to be teaching you how to do Solana programming with compressed NFTs. And there's timestamps on the video, so feel free to skip to the most relevant parts. So I created this pull request to the Solana program examples, and this is the one, if you are wondering, Solana developers program examples. And in my pull request, I'm demonstrating, how you can do a cross-program invocation to the bubblegum program, and this is made by Metaplex. So all the minting of the compressed NFTs goes through the bubblegum smart contract. So let's say you actually wanted to implement your own custom logic. So maybe you wanted to attach some extra state onto the NFT. And so if you wanted to do that, you would have to wrap the minting instruction in your own Solana smart contract. So yeah, this is basically why we're doing CPIs, cross-program invocations. We want to do our own stuff, and then we also want to leverage, the stuff that other people have built. So yeah, this is basically what I've done. Just doing a simple CPI to bubblegum, nothing crazy, and also verifying that the person who wants to do an instruction with this compressed NFT is the person who's actually owning the NFT. So yeah, this is the verification part. And yeah, you can go through the repo yourself. I'll post a link in the description. So yeah, that's about all, and let's dive into how it actually works. So everybody talks about it, but nobody really understands it. And here I'm going to be presenting to you my, I guess, a very basic understanding of how compressed NFTs work. To preface this, I am the technical co-founder of Blessed Burgers, and we're going to be launching the Blessed Burgers PFPs. So these juicy burger PFPs. And let's say that we actually wanted to, represent this as compressed NFTs. And by representing, I mean just minting these as compressed NFTs. So then what is actually going to happen? Okay, then we are going to be submitting a transaction to the bubblegum program. And then what happens on the back end? Basically, what is going to happen is you will have created a tree, a merkle tree at first, before we actually did it. I'll also talk about that in the code. But yeah, basically what is going to represent a NFT collection is, these merkle trees. And this is very different from, what we previously knew about NFTs, because previously it was just like, okay, I made an NFT and then I store everything as an account on the Solana blockchain. And yeah, that's going to be quite expensive if you do this for, each and individual NFT. So what is going to happen here is we mint a compressed NFT, and that basically just creates a new entry onto the tree. So a new leaf is created here. Yeah, that is quite simple. And this is going to be, this tree here, this tree structure is going to be stored on the Solana blockchain as an account. So far, so good, I think. So yeah, then comes my very basic mental model of what the Solana blockchain is, and I guess what most blockchains are. Not too sure, but I'm just a Solana maxi. I only know things about Solana. So basically what the Solana blockchain contains is all of this account state. So just like data, you can think of it as just like data on the cloud, and this data is something that you can easily access. All right, so I just increased my mouse size, and yeah, I talked about account state. So yeah, basically this is all the data that you can store on the Solana blockchain, and you can easily access this data. And this is also the objects, the data that the Solana smart contracts are going to interact with. So yeah, there is that. And then you also have the ledger, which is just, all the transactional logs that, has happened on these account states. This is going to be a very long, block of, I guess, chain of blocks, as per the word blockchain. This is just like all the transaction data that has happened throughout the beginning of time, and all of these transactions have talked to the account state to denote, okay, what has happened. So this is like the very brief understanding of what it actually is. All right, so with that said, let's go back to the tree and start from the beginning. We mint a compressed NFT, which means we create a new leaf on the merkle tree, and the leaf itself doesn't actually store any data. I guess it's just a reference to, what it represents, which kind of NFT it represents. So then we are going to take the NFT metadata and, all the data that, goes behind representing the NFT on the tree, which also includes, some merkle tree specific stuff like proof hashes and stuff like that. Maybe they don't need to know all of those details, but basically all the things that are surrounded with representing this NFT on the leaf. The leaf doesn't store this data, so we have to store this data somewhere else. And we take that data and store it in the ledger. And that basically means we are just going to put it there and forget about it, because now we know it's there and we could theoretically just retrieve it if we wanted to. But this is just to, ensure that we don't get super expensive, NFT data, because storing it in the state over here is expensive, but storing it in the ledger is super cheap. So yeah, we send all the NFT metadata to the ledger, which is going to be through the special no-op program. I guess you don't really need to know that much about it, but yeah. Essentially what is going to happen is, if this wasn't clear enough, all of the NFT metadata will just be stored in the transaction logs. And this way you have proof that it exists and that it was created, but you can't really access it easily. So then we've established that, okay, it's cheap to store on the ledger, but it's not easily accessible. So how do we actually access it? So enter the RPCs, because these RPCs are basically, computers that interact with the Solana blockchain. Every time you make any request, make any transaction, it goes through RPCs and they communicate with the blockchain. So these RPCs are responsible for indexing the NFT metadata. So they actually store the things that, was stored on the ledger. So it's kind of like duplicated data. So once on the ledger and then once at the RPC level. And that means every RPC actually has to store this data. So it also can get very expensive for the RPCs to host this data. Basically, what is going to happen is, okay, the NFT has been created and we store the NFT metadata at the RPC level. So that way it is easy to request the data and view the NFTs in your wallet. And this is also kind of like the confusing part about, is the compressed NFTs actually on-chain or off-chain? And the answer to that is, I would say both, because you have two parts. You have, the verifiability of the ledger, which is, I guess, on-chain, but then you also have the off-chain data, which is indexed by the RPCs. So that's basically how it works. And I hope this was a decent explanation. So here we are in the cUtils folder and the test folder under the setup. because we have to do some initial steps to test it out. So first of all, we need to create a tree, and here, depending on the specifications on the tree, it has an upper bound of how many NFTs you can hold within that tree. And yeah, there's that. So this is the tree that is, going to contain information about each and every NFT. So then we have the tree here, we save the address, and we going to create a collection, which is just for every NFT collection, there's also a collection NFT. So I guess I'm not actually really sure about this, but there's going to be some kind of like global collection NFT that represents the collection. At least that's my understanding. So then there's some UI for that. Oh shit, I forgot to mention. Never mind. So here we create the collection and save that collection mint. All right. So then after that, I guess we can run the setup. Let's do the thing npx. Do I have it here? I do. It's not called main, it's called test. Wait, setup. All right, so let's see what happens here. All right, nice. Something is happening. Okay, we've created a merkle tree and we have created a collection with this mint address. All right, nice. So then we can do a mint, and this is the test for that. We have the unit test, some minting here. So this is the instruction that does a cross-program invocation to the bubblegum program, and we have given it a just dummy UI. This is going to represent the metadata of the NFT, and yeah, let's try it out. So let us execute that and do a mint, and it should appear in the test wallet because the test wallet becomes the leaf owner. So yeah, let's try it out. To execute the test, you have to, where did my thing go? I usually don't use this terminal, but for demonstration purposes, I'll just use it. Where was I at? Okay, clear. All right, anchor should be here, not this one. Oh my god, it's lagging. Okay, skip validator. All right, here we go. So now we'll be minting a NFT. Nice. All right. Oh shit, I was supposed to comment out this one, but I think it works anyway. So let's do the minting again. Clear, and let us see. All right, so here, this is on devnet, by the way, and let's check it out. Oh, this is the signature. Good thing I have some bookmarks. Pro tip, by the way, always have bookmarks for the different clusters. All right, so something happened, and we are in our own smart contract. This is the program that I have deployed already, and we can see that it invokes the no-op program, which is the program that is going to store the NFT metadata on the ledger. Basically, what it does is it is going to put the NFT metadata as instruction data in the transactions. So yeah, this is the I think this is where all the NFT metadata is going to be contained. Although, at least this is my guess. Yeah, so we can see quite a few calls to the no-op, but I've heard that the no-op program is quite OP, as in overpowered. Yeah, then we can see that it also invokes the state compression program, which is the bubblegum program. And we can see that it should be here somewhere. Yeah, here we go. Bubblegum mint to collection. Nice. All right. So we can see our mint as well. Let's go to WebStorm. We can see our mint as well on Solflare. So basically, we have minted the compressed NFT to the Leaf owner, and the Leaf owner is test wallet, and we have saved the test wallet in the test wallet JSON. So you can actually, this test wallet JSON contains a private key, and you can import the private key to your, not your wallet of choice or wallet of preference, because currently only Solflare supports compressed NFTs on devnet. So yeah, you can go to Solflare and import the private key, take the private key from test wallet JSON, import it to Solflare wallet, switch to devnet right here, and now you can see, great, we have minted some compressed NFTs, and you can see that these were, some of them are from previous tests, but yeah, this one and this one is definitely new, and you can view the NFT in the Explorer as well. It's not going to show you anything because this is just the assetId, basically just the node, the leaf in the tree. I guess this pub key represents that leaf. So instead of having mint addresses that we knew from before, these NFTs are going to be having, you know, the asset IDs, and these asset IDs are retrieved from, you know, the merkle tree itself from which it was created, and the number, the consecutive number of, you know, the number of NFTs minted. I hope that made sense. Maybe it'll be clear in a bit. So yeah, we can see that, nice, it happened successfully. We minted through our own smart contract. Nice. All right. So then there's the other part of, you know, verifying that that you're doing a transaction, and you want to make sure that the owner of the NFT, the owner of the compressed NFT, is actually the one who is you know, doing some stuff with the compressed NFT. Otherwise, you know, everybody could, what I'm even saying here, we just want to make sure that the owner of the compressed NFT actually signs the transaction. That's what we want. So we can do that. This is quite hacked, but yeah, what I did was just comment out some code, and then on comment this code, and then we can basically take the asset ID that we just had, and we can put that in here and verify that you know, that we are doing a transaction on a compressed NFT that we actually own and want to potentially modify. So yeah, here the signer is test wallet, which is the wallet that actually owns the NFT. So this should be okay. This should pass successfully. Let's test it out. Running the anchor test again. All right. Okay. Damn it. Oh shit, I forgot to replace my RPC. So yeah, that's the other thing you need to do. You need to go in here and you need to insert your RPC path. This is, you know, because the RPCs are storing the NFT data, as mentioned in the technical overview. So let me paste that in real quick. All right, we're back with a RPC. You can choose either, obviously you would have to choose the RPC providers that actually support compressed NFTs. So because we didn't have a proper RPC, we couldn't fetch, the data that was related to the NFT. So now that we have that, let us do the test again. And success. Let's actually go and view the transaction. Let's see what's up. All right, so we called our own smart contract Verfiy something. Yeah, so this was verified. We signed a transaction of including a compressed NFT that we own. So what happens if we don't own it? This is the question. So let's say I'm signing. Currently I own this compressed NFT. Burgers are coming. Burgers gonna murder. Hide your kids, hide your wives. This amazing compressed NFT. Shout out to BurgerDAO. This is, the owner, but what if we had a different owner? Could we still do stuff in the program transaction, in the program instruction? So let's see here what is happening. Okay, now we changed the signer, so this should not go through. Let us see. All right, we got a failure and it says unknown signer. Okay, now we know that, okay, if we wanted to program this stuff, we could actually enforce that, we wanted the owner to sign the transaction. All right, so let's actually go through the some smart contract code, and basically here we have the deployed program starting with Burr, because if you know, you know. And yeah, we have these two instruction endpoints that you can use to interact with the contract. And yeah, let's check out the minting instruction. Basically, this is a wrapper of the bubblegum program, and since it's a wrapper, it has to, accept all the same accounts as the, bubblegum program. Makes sense, right? So the idea here is that, okay, we want to do something extra, and let's say we want to, create a PDA as well. So the idea here is that we can initialize some extra data that references the compressed NFT. And the seeds for this PDA would be something that, would do the reference. And the way that, it works with a compressed NFT is that the merkle tree and the nonce would be uniquely identifying the asset ID. So maybe you could even put the asset ID as the PDA seed as well. So that is the idea. Maybe then you would do some other, stuff in the logic here, maybe logic, if I could type. Yeah, and you can see that, okay, it actually takes many, accounts in the instruction and the context. So this also limits how many extra accounts you can work with. So then I would also recommend working with version transactions to, boost the amount of accounts you can have. And these 6 accounts, you can basically just put it in the address lookup table of the version transaction by default, I guess. So that way you already minimize quite a few bytes. So let's check out the Verfiy as well. This one is also super simple. It's doesn't really take that many accounts. But here we make sure that the owner of the NFT actually signs the transaction, which is what we had before. with the test that didn't pass with a incorrect signer. And here we give all the the off-chain data provided by the RPCs. These are going to be inputted to the instruction for the NFT verification. So basically, yeah, you'd have to construct the leaf based on that input, and you would send it to the compression program to check, okay, is this actually a legitimate leaf in the merkle tree? So here we do a cross-program invocation to the compression program as well as with the remaining accounts. And the remaining accounts are just the proof hashes that was retrieved from the RPCs. All right, so I think that is pretty much it. And the idea here is that, after doing the verification, you would then continue to do your own, custom logic from here. So here we will do some logic as well. All right, so I think that is pretty much it. I don't have anything else, so feel free to leave me any questions on YouTube or on Twitter, and I'll be happy to answer. Stay blessed.